Okay, I think we can get started. So thanks everybody for coming to the Marine Science Seminar. I'm happy to introduce our guest, Arne Diercks, who is with us with the School of Ocean Science Engineering as a research associate professor. Arne got his first degrees in Hamburg, Germany, and then came to USM to do his PhD in geological oceanography, and he actually has the distinction of being the first PhD graduate from our program. I won't say exactly what year that happened, but after graduating, he moved into the commercial sector for several years, but still in the area of marine technology. Eventually, he moved to manage the AUV program with the National Institute for Undersea Science and Technology, NIUST, and that brought him up to Oxford, Mississippi. And he started officially as a research professor at USM in 2014. So today, I believe he's going to be talking about some results from one of his recent GOMRI projects. And I've had the pleasure of being on the committee of some of his graduate students. So I'm really glad he's taken the chance to share his work with you here today. So go ahead, Arne.
Thank you, Chris, for the introduction. That is, yes, the data I'm talking about are going to be from a project which was funded during the RFP6 round from GOMRI, and it is part of the title, the resuspension and redistribution of sediments in the deep Gulf of Mexico. And I have a whole bunch of co-authors, everybody on that cruise. That was a 14-day cruise out to the southeastern Gulf of Mexico. Did everything from collecting samples. It was two teamwork out there, and it was a fabulous cruise. We got great data and great cores out of it. I'll show you some more in a little while. And Austin is actually working on these cores and is hopefully getting soon to the part where he is finishing up with his master's thesis on this. So back in 2010, I'm not sure who all knows about or how much you guys know about 2010 Deepwater Horizon oil spill. The surface expression for this oil spill is this very, somebody's microphone is open, big spot here, which is the colored, basically the highest concentrations are in this area, some extent going to the southeast, but in general, a northeast, southwest distribution and a big glob in the middle. The black dot there in the middle is the Deepwater Horizon site. So what happened there? While we were out there with Werner and I, when we were out 2 weeks after the cruise, we found, 2 weeks after the spill, we found these flocks, marine snow, whatever they called it at that point. We called it marine snow, not knowing better at that point. We knew it was somehow related to oil, but a lot of material was in the water column. In beginning looked like this, and then it changed into shapes like this. I took those pictures back in 2010 on the Pelican cruise there, and it was dubbed later on into marine oil snow or marine snow oiled marine aggregates, or marine oil snow sedimentation and flocculent accumulation. That's a mouthful. In a workshop published later on by Dali in 2016. So that was the idea, that this is all oil-related marine snow, which then somehow ended up through the water column on the seafloor. And that was basically took the surface oil down to the seafloor and deposited there. And that at that point was, well, that's it. The oil is out of sight, out of mind on the seafloor, done with. Now, the question which came up in some discussion we had out there, was this really, is this all there is to the MOSFA event, or is there still something else going on happening to this oil? So there's a little summary there. The basically MOSFA event disappeared and from the water column and cleared out the water column really pretty from green to perfectly blue out there. We were out there while it happened. And this event happened within a short amount of time, weeks to months. And it deposited a detectable layer of oil on the seafloor in the centimeter range. And the general original sampling strategy by NERDA, by the National Response to this oil spill, was in a specific area close to the site. I'll show you in a minute. and it was limited in spatial distribution there. But we'll get to that in a second. So what do we believe this marine oil snow actually, what happened there? How did we study? This is a graph we did in EcoGig, another one of the GOMRI consortia I was part of. What happened to the snow and how did it get its seafloor? This whole process. We had basically a leak on the seafloor, well, an oil spill on the seafloor coming up, putting the subsurface plume out and going up. This plume went southeast, southwest, northeast direction. And then we had the surface expression of the oil, which was due by phytoplankton, bacteria. All this stuff was degraded, accumulated, and eaten up by fish, and basically stuff got moved down to the water column, which we collected in sediment traps material, and I collected camera data with this, and it was brought down to the seafloor and then deposited. What's missing here is resuspension. So the idea that the material on the seafloor is not stationary. We know that we have currents in the water column, and we also know that these currents from publications are strong enough to actually move material once on the seafloor. So to the sampling, quote unquote, bias here, these are the NERDA coring sites, the red dots. The green dots, oh, yellow one showing up already. The green dots are, these are C-image sites. This is mislabeled. And the yellow dots are actually EcoGig sites. So those two labels got switched. So this is, again, you can see the sampling basically following the direction of the subsurface plume, southwest, northeast. What's missing are sampling in this area right here, where we believe and proposed to look for oil, which was persistent, initially deposited here and then later on moved into this direction. So this is basically the big black hole there of material, which we don't know what is there. So the seafloor footprint originally published by Jeff Chen in 2015 et al., which shows basically, again, the northeast, southwest, and we find, based on his numbers, between 1.5 million to 19 million of gallons of the oil was deposited on the seafloor. He estimated in this area right here. Similar one in Romero et al. Calculated a little less. She got between 4.2 and 3.8. What? That's wrong. This is 2.2 and 3.8 million gallons. So this, don't look at the 4 there. It's not there. So that is basically between 2 and 3.7% of the oil got deposited, again, limited on the NERDA sites and the available sampling sites, collected or deposited in this area and along the shore's coastline. That is the idea we had when we started out this project. Now, back in 2016, we had a little, we have a marine snow camera, which is basically a camera system with a flash on it, which is being lowered through the water column and takes pictures of marine snow. And that camera was deposited on the seafloor on accident and took some beautiful pictures. That was back in 2016. So you can see there's time between these images is 6 seconds. The camera was simply set on the seafloor. That energy introduced to the seafloor was enough energy to produce these images. This is 36 seconds of images. So relatively quickly, this whole thing got messed up and material got very easily resuspended. And it doesn't take much energy to do that. So what happens to the material? I had to make this little movement there. It gets resuspended, and then later on, it gets redistributed and then redeposited. Let's hope that this movie plays here. Is it playing or is it not playing? Oh, it's not playing. Is it playing, the movie? Huh.
It's going.
Anyway, it's going good. It doesn't show up my screen. So this is basically a surface. We had a flood here a few years ago, and this is simple water running across the street. That's not the seafloor. There's no trees on the seafloor. But this shows nepheloid layers in fresh water being transported with the currents. And you can see how they change shape. They are not steady. They are not evenly distributed. They are completely localized, some of them, and they are not unanimous everywhere the same. So they are really multifaceted features to these nepheloid layers. So now, how do we study resuspension sediments on the seafloor? On the surface, I take a camera and just take a picture outside the car. But at 3,000, 2,000 meters water depth, we can't do that like this. So we have to use different instruments for this. So we are using sediment trap systems, which augmented with cameras and current meters. So we have 2 sediment traps. We have a flux camera, which takes time series pictures of material arriving in the trap over time, the current meters, and then releases on an anchor down here. So with that, we can identify events which happen on the seafloor where material is being brought into these traps or into the flux camera. For now, we look at the traps, these 2 stacked traps, which are about 90 meters apart, close to the seafloor, 30 meters above bottom, which is the seafloor. So we were able to detect with these 1 mooring we had out there at, near the Deepwater Horizon site, 3 different ideas of sedimentation events or resuspension events: small-scale local ones, small-scale far-field ones, and large or hurricane-scale events where we get tons of material. I get to that more definition in a second here. So how do we differentiate between primary production, surface flux, and resuspension? Say we have material coming from the surface constantly coming in there. That's where the sediments come from, most of them. And how do we take this apart and say, yes, this is resuspension, this is not? So we're looking at the particular organic carbon content against the sample dry weight and lithogenic silica, basically quartz sediments. So if we compare the particular organic carbon against the sample dry weight, then based on the knowledge that we have that biogenic material being deposited on the seafloor, once it's down there, it's starting to be decomposed, bacteria, and things are falling apart, and the organic carbon, if it's being consumed, and so the relative amount of organic carbon per volume is decreasing. So we have sample dry weight with low particular organic carbon means we potentially have resuspended material which has been deposited on the seafloor and then got moved back into the water column and then settled back into the sediment trap. So basically 1 cycle more. Again, same thing as if we have lithogenic material, or lithogenic silica is a good indicator for resuspended material. The more lithogenic we have, either it's a river input, but again, it is bound in coagulates with aggregates or stuck together and is not easily resuspended. But in general, we assume that lithogenic silica is a good indicator for resuspended material. So these stacked sediment traps, we need 2 to do this whole thing, not just 1. Now, 1, we can differentiate between the resuspension methods. So if you look at what the data we get from these 2 traps is, first we get a time series. We get material, these bottles, these are 21 bottles underneath the trap there. These are 18 days of sampling between these samples of the sediment traps. You can see events of lots of material and getting low, 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 low. There's a hiccup there, there's more there, and then again, and lots of events again. So 18 days between bottles. So we can determine spring blooms, storm events in general, but these are 18 days of time averaged samples. So not very high resolution in this part. Now, if you take the same samples and look at the, again, previously mentioned POC and dry weight ratios, if it's a high particular organic carbon, we have probably an input from the surface with fresh organic material primary production. If the ratio is low, means there's not much particular organic carbon in there, we assume that we have resuspended material from the seafloor. Same thing with LSI or lithogenic silica. We can get information about different source material. If you compare the 2 traps, if the bottom one, if only the upper trap gets material, but not the bottom one, we have input at 90 meters above the seafloor of material which is being advected into the area and settles out slow enough that it does not reach both traps. And it's a very short event. So it's a small scale event like this little material being brought up and it's being drifted to the side and then settles out, but it's not fast enough to reach the bottom trap. If we have the same effect on the bottom one, but not in the top trap, we have a near field or a local small scale resuspension where the material is not being moved up far enough in the water column that it can reach both traps. So we call this a near field small scale event. In the event where we get these resuspension in both traps, or we see material in both traps of the indication that being resuspended, then we call this a large scale or hurricane scale event. And we had the luck that we had actually a hurricane Isaac coming across the moorings we had out there. This is GC600 down here. This is a very large scale. This is between 600 miles here, something like that. What is that? 61, 2, 3, 4, 5, 600 miles east-west, and then about 180 miles north-south, roughly. So there's OC26. That is the mooring with the double stack traps. The Macondo well is right there. PC345 are particulate camera data. I'll show you in a minute. And these M1 to 6 are coincidentally the Geyser Gomi Consortium had 6 current meter moorings out there. So we had a plethora of current meter measurements right around the site. So we actually could support our ideas about resuspension with additional current meter data than just our own. So back to the classification screen, we have, if we look at the, let's bring it in quickly. If we look at the far-field small resuspension, if the upper trap has more LSI relative to lower, we have far-field small resuspension, and then small near-field large resuspension events are the opposite of the scale. All this stuff is in a publication in the Elementa. So if you now look at these 3 camera sites and we compare the camera profiles, which is basically 1, 2, 3 camera profiles, panel B and panel D are comparison what happens between these 2 sites, or 3 sites, or 3 stations. We get a particle abundance profile in different size classes down to about 1,250 meters. There's not many particles in the water column. And then below that, we have a very big nepheloid layer of particles between 1 and 1.5, and some 1.5 to 2, and then it goes up somewhere in the range of 2.5 millimeters. So it's getting a little bigger. There's not many small ones in there. There's a lot of larger sized particles in the bottom. Then we move to particle 4. We see sudden camera profile 4. We see particle sizes 1, 1.5 got majorly increased, smaller got majorly increased, and larger particles got increased as well. So we can see that there is a loss in a very large fraction down here, relatively. See the red ones took off, and we have lost those, but we gained very small and 1 to 1.5. So we gained these particles. Then comparing PC 4 and 5, we have an opposite. We're losing particles in the bottom nepheloid layer. So something happened to them. Either they got deposited, they got removed, and they got moved. So we don't know exactly what happened. So we can only say that changes of particle concentrations and numbers per liter changed between 1.5 days. There is a time difference between 1.5 days between PC3 and PC5. And that whole thing happened. These whole stations were taken about 1.5 weeks after Hurricane Isaac came through. So let's relate that back to those images of the camera frame. They came in really handy. If you look at it visualizing this whole thing, PC3 is a normal particle distribution with a nepheloid layer. Then the difference here means an increase in fine particles, really blurry, loss in large particles. Then PC4 is a mixture of all of them. It's very increased, lots of particles, lots of large and small particles. Then the difference here is we lose a lot of particles, and we have in generally much less particles. And then, sorry, this one here, we lose particles, we have much less than here. And PC5, then we have in general a different composition. We have large particles, small particles, but in generally a different composition again than we had before. So it changes over time. Conceptual idea. So this is, these are the current meter data. My computer just froze. Hold on. There we go. So these are current meter data describing from M3 and OC26, showing that we have the general direction of currents in here, pointing towards the current in this part. We don't look at MP4 and 5, 6 because they are too far away. M3 and OC26 are the ones we are interested in. And then if you look at the time scale, which is basically the bottom line here, this line here is Hurricane Isaac coming through. And then we have a backwash coming in at these sites from shore. And then a few days later on 9, 12, 13, 12, and 14, we have the camera profiles PC3 to PC5. So that is Can you still see me?
Yep.
Because my computer is just not giving me just. It says piece of PowerPoint just made an error here. It's waiting to come back up.
If you need to restart, that's okay.
Hold on. Maybe it's going out now again here.
Is it a large movie loading?
No, I don't think there's a large movie. It's just a map.
Okay.
But it says micro points not responding. Wait for the program to respond. Shall I restart? Do we have the time?
Yeah.
All right, I'm bringing it back up. I'm sorry about this. This is my fun here with this. So we were at slide. Let's go here. Present, and then I have to share the screen again. Share screen. Can you see this again?
Yep, looks good.
Okay, so the M3 and OC20 and OC26 sites are, M3 is up on Mitchell Dome, which is this is a bathymetry map showing the darker the colors, the deeper the bathymetry in this case, going down to 2,000 and 1,000 meters up here. OC26 mooring is here, Macondo is here. This is about 6 kilometers, 7 kilometers south of Macondo where the mooring was. But it was in the between two domes, Biloxi and Gloria Dome. And so that's the reason why we chose M3 and OC26 mooring to compare these sites. If you look at the zonal meridional flow of the current meters, you can see that there is increases in, let me get my mouse, the laser pointer here. You can see that we have, this is the hurricane event. These are the colored light greens are near field resuspension events, and the dark greens are far field. So you can see that we have different events coming up at both sites, and they are current speeds are indicating that the sedimentation of the events we had in the sediment traps could be related to the currents we had coming through. Same thing at M3, the geyser mooring. Again, we have the 6.5 centimeters per second speed is flagged off. That was an indication from literature where it would actually resuspend material. And so we have our data that we collected from the EDCP data, as well as the geyser moorings, are indicative that we can have resuspension induced by these currents on the seafloor. And we calculate bed shear strength at both sites. Again, the time intervals where we see highest bed shear strength events coming through coincide with the events of our resuspension events we calculated. I'm going a little quicker through this whole thing. So if we take an 18 days and do a basically a time series stacking of 18 days of currents, we can see that the per size, this is M3, this is the mooring. We can see that basically the transport over time goes to the southwest. This one is a different side, it goes down to the southeast. So this is one thing to remember. But both for these sites, it seems we have a transport. Some of it goes to the northwest, but we have in general transport to the southeast. Okay. M3, M1, so on. Okay. So if you look at a 3D model, it looks like this. Same thing. You can see that we have high domes around the sediment trap, which would allow us to say, yes, we do have far field resuspension, which only hits the top trap because, well, it was resuspended further up the slope or on top of the domes. And in this case, M3 shows that we can resuspend material from Gloria Dome and move it over to the trap, and actually is only deposited within the top trap, possibly. So if you do a flux polar diagram with flux, we can see that most of the stuff is being transported to the west-southwest. But you always have to read the fine print. There is some southeast component in there, or east-southeast component. And that is where we came up with the idea of our GOMRI project, and where we collected cores. So during that sampling cruise, we went to the southeast. We took the high resolution bathymetry which was published in 2017 by Kramer and Shed from Bohm, and did collected or looked at sites based on seafloor morphology. So I created or modeled a watershed analysis based on this very high resolution bathymetry. And what you see here, the different colors are basically giving you slope angles on the seafloor. The lighter the color, the lighter the color, or grayer the color, the flatter the seafloor, and then you get these high slope angles up to the north west. So 84% on the seafloor actually are basically flat. I mean, really flat, 0 to 2 degrees of slope. There's nothing there. The black and blue dots are our sites we collected. If you take it down to even smaller, less than 1 degree, it's 57%. I just click through these things, basically split up. What we can see is that the slope angle increases the further northwest we go. See, there's almost nothing down here left. It's all basically up in the northwest, closer to the deeper horizon site, around these domes, these morphological domes on the seafloor. Now, if you take the other part of the model, which you actually get something called streamlines. Basically, they show you the gravitational flow based on morphology. So in general, if you would basically have no currents, nothing else, you put some water here, it would flow this way. And that looks this way in a little 3D model. You can see it a little better. The Macondo well sits right here. This is Gloria Dome, Mitchell Dome here. I forgot his name again here. Anyway, so the flow is basically going to the southeast. From here, all these are the same flow lines. If you go the other way around, you look from the southeast to the northwest, you can see little valleys in there. The seaflow morphology is highly exaggerated here, just to show the individual channels, quote unquote, how the morphology looks. It is not this exaggerated, it is flat, but there are streamlines within the 5 to 10 meter vertical acceleration over a certain distance. You can calculate them and you get these streamlines out of it. So based on these streamlines, or these data we have, the angles plus the streamlines, we went out and we said, okay, we want cores here, 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 here to try to trap or define different sedimentation regimes. We call them the depot centers, open plain depot centers, erosional valleys, stream channels, isolated valleys. So you can see some of them in here have these channels, erosional channels between them, depot centers. If you look at the depot center, this is the cross section through one of those mountains. You can see down here is the site. So it's very flat. It's actually really flat, 0.1 degrees. There's not much there. This again is exaggerated to show the idea. This is a little more. This is now going from here to here. And you can see we are on the lee of this Gloria Dome here. And the site is here. So we have a 2.4 degrees average over the entire length. So this slope is much deeper because we're averaging all over that. So we can tell that there's differences in these sites. So again, we have depot centers between the streams, out in the plain, open plain depot centers, because this is the really deep water. We are now between almost 3,000 meters. This is in the deep Gulf. We have depot centers, stream depot centers. So you can see the differences in the morphology of the seafloor, and we have different depths in there. During the cruise, we went out and collected perfect cores. I think they're perfect because we have clear water above. We have a perfectly maintained interface, sediment water interface on several cores. We have a couple ones which were not quite as nice. We have differences in sediment structure on the surface and how the fluffy layer here, you see a very thin layer. There's not fluffy material there. This could have been disturbed. So what do we do with these cores? We ran them through a designed sediment flume to figure out what the erosion of material is on the seafloor. How easily can we erode this stuff? Because that tells us how much material we can move relatively, and is it moving at all? These are the cores stored in the container, nice and cold. Then this is the flume Austin and I built. This is sitting in the 1029. It is actually a water tank with water flowing through. This is the flume. It's a closed loop system. And once we put the plug in up here, it is completely closed. We can not pressurize it, but anything we do with the pump down here is immediately transferred to the flume. So we don't have any spin up time, or we don't introduce air or anything else into the system. That is some more pictures you can see during introduction of the flume. We took very much care, or Austin, not we, Austin did, of not taking the or disturbing the interface. He'll tell you more when he's defending his thesis. But in general, we took videos of it. There's the video of the flow. It shows perfectly turbulent flow in the system. If you can see it, I'm clicking through further because this is now this is a video on top of the core. You can see material being moved off the core at certain very low speeds currently, but we can tell that material is being removed. And what we then took is the video of these particles coming by, and we analyzed, this is from Austin, we analyzed the pictures with Image Pro to get data over time of particles, which then look like this. And that's the reason why I went so fast. So this is a poster Austin presented at the Ocean Sciences meeting in San Diego. And it shows basically differences in particle resuspension based on shear stress. It shows you can clearly see the difference in here. This is what we call an erosional valley. There's not much coming off material at the beginning over time, shear stress. So increasing flow this way and particle count going up or total volume. Same thing over here, roughly the same scale. And so much more material coming off at much lower speeds. So how do we relate this to depot centers? For us, if the change is in speeds and erosional forces are there, and you get more material at lower speed of the ground, that means there was more material deposited, which was not very consolidated. So low flow speeds and most likely a depot center. If the material as an MCO8 takes a lot of energy to remove, either the fluffy layer, which is in most of these cores we see, is no longer there, or the material is very consolidated, or it has a lot of organic carbon in there, or any kind of glue which keeps the stuff on the floor. So lots of possibilities. So it's very hard to determine. Again, these are showing some more across the same thing with the flow and depot center. This is MC19. It's a depot center right behind the hill. I didn't calculate what slope it is, but this is an open plane. And sorry, this is a flow, and then this is in the depot in a valley here, basically where stuff can be easily deposited. So this is material comes now. This is not published. We're in the process of publication and are writing currently on this. So please.